Physics 3030, the universe. This is lecture 13 in the series, and today we're going to talk about dark energy. We are getting pretty close to the end of the class here. And we'll talk about flatness, and flatness in the sense of the curvature of the universe and the amount of matter in the universe, how those things are correlated. We'll talk about the expansion of the universe and how measurements in the late 90s showed us that the expansion first found by Hubble is actually accelerating. And then we'll talk about why we think this is caused by something called dark energy, though we don't really know what dark energy is. And then we'll talk about something called the Lambda CDM model of cosmology. Okay, so we've spoken of curvature before. And we're talking about here about curvature of space-time. So all four dimensions that we live in. Okay. And we know that it's flat. We know that overall, if I look at the entire universe on average, no universe is very flat due to measurements that we've taken. And one of the main reasons we know that is, again, because of the cosmic microwave background radiation. Okay, and your book goes into a lot of detail about this, but we can look at the correlations of different parts of the CMB. So where are the hot spots and where are the cold spots? So correlations of what are called the anisotropies. Right? Remember isotropic means it's the same in all directions, and isotropy is a little bit not the same in all directions. And so these are the maps that we always see. And so you look at these correlations of anisotropies by degrees, by angular degrees, right? And the idea is if I have a hot spot here, what's the chance that the next spot over is hot as well? And if you look at this correlation graph, there's sort of a graph that looks like something like this. There's a big peak, and there's like a little peak down here. And the biggest peak is at about 1 degree for how correlated these things are. And if you do the math, if you look at the particle physics, okay, this 1 degree implies that the universe, nice change color in the middle there, is flat. That's where the highest correlation should be in a flat universe. It would be a little bit smaller, I think, if it was curved one way, a little bit bigger if it was curved the other way, and flat is right around 1 degree. Okay, so we know that this is one of the most accurate measurements that we have of how flat the universe is. And this is called the angular spectrum. Angular spectrum. That's what this graph is called in your book. Okay, so we know that this is true, and we also know from this sort of what the proportions of matter and energy should be. Okay, all together. Remember, E equals mc squared, so they really are just lumped together. Should be. And we know what they should be. Remember this idea that if there's this thing we call omega, and if omega is 1, that implies flatness. Okay, and we know that omega is 1. And then we look at how much stuff we have to have. We know that omega is 1, but we look how much stuff we have to have for the energy density of the universe. And if I look at all of baryonic matter, remember baryons are things with nuclei, okay? This is baryonic matter. This only makes up 0.04 of that 1, which is equivalent to 4%. Okay, this is all of the baryonic matter that we ever see. Okay, And if we count in dark matter, we get another big chunk. Okay, that's 0.22 of that 1 that's up there, upstairs, and that's correlates to about 22% of all the stuff in the universe. But of course, the thing that's missing here is that if I add those together, there's still we're still missing about 74% of the energy density that we need for flatness. Okay, so this is the idea that we have this ratio. We know that the ratio is 1 when the universe is flat, and it's a pretty fine line. We know that that flatness, part of the flatness is explained by the fact that the universe went through this huge exponential expansion that we called inflation. But we know also that there has to be a certain amount of energy density. Okay, that's what that 1 is really telling us. And so we know that if I look at how much of that 1 is made out of baryonic matter and how much of it is made out of dark matter, which we don't even know what dark matter is, but we know how much there needs to be around stars and things like that to make the math work, there's still a missing chunk. This is 3/4 of the universe's energy that we just don't know where it is. Okay, and let's move to this next slide here. We'll show you what the proportion is. Of course, we call this dark energy, and you can see the numbers. Everybody's numbers don't quite agree perfectly. Here, this is 73% instead of 74%, but 1%'s not bad. Notice that only 0.4% of the universe is made out of things that really give off light. A lot of it is this intergalactic gas, okay, way more than the stars and planets and stuff. Then there's this chunk that's dark matter, and then, of course, this huge, huge percentage that is dark energy. Okay, sort of the pie that people show often. You've probably seen a picture like this. So this is what we know. That's how we know that there has to be so much dark matter. And so okay, so we know that 74% of the energy density is missing. And one of the things that we weren't sure about, or we knew about all of this, is that this flatness idea, this flatness condition, it relates to energy density, so how much matter and energy there is in the universe. That's what I was just talking about. That's what we call omega, right? And this all relates to the expansion. Okay, remember that we said that we know one of the reasons we know that this is flat is because of this exponential expansion after inflation. And even the current expansion and the rate of expansion and all this stuff has to do with the flatness and the energy density. So one of the ways in which scientists tried to understand what's going on here is to try and study the expansion of the universe. Okay, and remember that we had a number of different scenarios of what the universe was, right? There was sort of a closed universe that would eventually collapse on itself. There was an open universe that would expand forever. And then there was a static universe, right, that just was in a steady state and wasn't moving at all. Okay. Oh, actually, these are not quite the best way to categorize this. This is just the flat. This is the flat one, and we still have expansion here, but it's at a constant rate. Okay. This is the Hubble constant, what we were talking about before. But then before all of this, right, sort of before this was the idea of so kind of putting it up in here, was the idea of a static universe that in the beginning Einstein really preferred, which was that nothing was expanding. Everything was just in the same spot. Maybe things were moving around randomly, but there was no expansion, no contraction. So that's a different idea about how all this works together. And this middle one here where we have open, expand, and not only do we expand at a constant rate, but this expansion accelerates. Okay. But of course we had a measure of the universe being flat, so we expected if we measured the expansion, then it would be at a constant rate. Now we know that it wasn't constant all the time. Remember that inflation was a period where we didn't have a constant acceleration, we had an exponential one. Exponential means it was increasing, so every time it expanded, it expanded faster and faster and faster. Okay, and so we've had that in the past. Then we had it slow down, so we had a period where it decelerated. So there was sort of, I can schematically write this like Big Bang. Okay, we have a Big Bang, and of course everything's expanding. Then you go into inflation, and then you come out of inflation, right? And in these two spots, you have an accelerating expansion, so it's expanding faster and faster, and here you have a decelerating. There's maybe two C's there, I'm not sure. Decelerating universe, and then sort of normal expansion here at the end. Okay. Now, we, of course, as scientists, want to corroborate this ideas, and we're assuming that it's pretty flat and our expansion rate is pretty constant, but of course it wasn't always constant, so let's measure it. And we're going to measure expansion. So how to measure expansion? Well, we want to compare everything to the Hubble constant, right? The Hubble constant is how fast everything is moving. So we want to compare the rate to, usually called capital H sub 0, the Hubble constant. And the Hubble constant really gives us a way of measuring how far away something is, right? Remember, if I can look at the redshift, which is proportional to the velocity, right? The faster the velocity, the more the redshift on the y-axis. And this axis tells us the distance, right? So if I know that this is some constant line, then if I measure a point here on the line, then that gives me an idea of how far away something is, right? I can look at the redshift, go over to this line, and then go down, and it tells me how far away it is. So this is one way of measuring the distance. Now, of course, this is comparing it to the Hubble constant, which we're trying to measure, so we need another way of measuring the distance. So, of course, remember that we talked a lot about the inverse square law, second or third week, okay? And this is how Henrietta Leavitt found used Cepheid variables to measure distances. The inverse square law is how Hubble actually measured the distances to these, but we need standard candles. Right? A standard candle is some kind of star we know the intrinsic luminosity of. And here we're going to use type 1a supernovae. Okay. And I told you a little about these supernovae. And the main point for these guys is that they have a specific spectrum and they really just don't change very much. So if I look at sort of the luminosity over here as a function of time, then they blow up, they peak, and they drop off. And this peak intensity, okay, is very characteristic of these type 1a. And you can tell, again, by the shape of the curve and everything else, what's going on. Because these type 1a's form in a very special way, there's something called the Chandrasekhar limit. When they get to a certain mass, they explode. They're neutron stars that explode. And we know their intrinsic luminosity. That's the important thing. So we have another measure of distance. So then we come over here and we compare this distance, right, to the distance from this guy, so the distance from the inverse square law, okay, and we see what we get. And a lot of people were doing this. These type 1a supernovae are pretty hard to find. They only happened like 2 per century in a galaxy, okay? And go to this one first. This is a copy of the data that's in your book, okay? There were 2 teams of folks looking for these supernovae, and it turns out that they actually, it was amazing, they only overlap by 2 supernovae that they recorded. And what you have to do is you have to kind of see them faintly start, and then you get a big telescope trained onto it so you can look at the whole intensity curve to figure out everything. And you want to get there before the peak, right? And so these are all the data points. And let's forget about the lines too much. Let's look at this top one up here. And sort of this is where you would expect things. I think this is a pretty hard graph to read. That's why I put this one up here. And this one, okay, the idea is that I'm really looking backwards in time. So we're sitting here. 0 is today, okay? And we're not sure what happens in the future, but we can look back in the past, okay? And remember that the further away we look, right, the further away we look, the farther back in time we're looking, because it takes light a finite amount of time to reach us, right? So the further these stars are away, the longer the light took us to reach us, so we're looking back in history, okay? And we sort of know what the Hubble constant is here, right? There's some tangent to this line, and we're comparing these guys sort of to that line. And they don't fall perfectly on a flat line, so you look at the statistics of this, and they fall onto this red line. So if I sort of extended, let's extend this blue line here again. Let's see if I can extend it. That's sort of the straight line that I would get, right? But they're not on that straight line, they're on this red line. And since they're on that red line, okay, what that means is, the slope of that line is, a little bit less than the blue line. And what that means is that the galaxies that we're looking at from further away were expanding slower. So the take-home message here is that expansion was slower in the past. Okay. This is a big result. This is a really important result. If it was slower in the past and it's faster now, that means we have acceleration. Okay, so the universe expansion is accelerating. And this means that something is going on. Something is a little weird here, because we thought, the universe is flat, so that means there's something in the universe that's making it expand. And we know what that stuff is that missing 74% of the stuff, right? And this is a weird thing. What it means is that somehow as space expands, there's something that's pushing space apart, right? So remember that if I had a bunch of particles together over here, they sort of attract each other, right? And gravity wants to pull them together. Okay, so you always have gravity trying to pull everything back together. Well, somehow as the universe expands, and there's something that's pushing it apart. So there's some pressure pushing the universe apart. Now, it's not as simple as all this. What's really happening is that we have epochs of the universe, and of course we had, so, if I go back to this, there's this huge acceleration here, and then there's this deceleration as it slows down, and that's because we had inflation, and then we have something that stops inflation, whatever that mechanism is. And so the universe expanded and accelerated and decelerated at different times in the past, okay? And it depends on the matter content of the universe, what's going on, and it just turns out that we live in the era right at this sort of inflection point here where you can start to see that the universe is sort of starting to pick up. It's sort of been expanding at a pretty constant rate for a really long time. You know, if I look maybe from here to here, it's pretty constant, and it's just starting to pick up. And we don't know why we live exactly at that moment. This is really interesting, called the fine-tuning problem that we're going to talk about in a second. Okay, so we take all of those different measurements of distance and things like that, and we note and we see that the universe is accelerating. So we have the sort of same question as we did with dark matter, and that is that there's something making the universe expand, and we just call it dark matter. Sorry, dark energy caused. Okay, and so dark energy is the stuff that causes this expansion. We don't necessarily know what it is. We know that it's that 74% of stuff that's making up the rest of the universe, okay, and that somehow it has this weird property of kind of pushing space apart as it comes. Okay, there's something called so there's of course a list of things that it could be, and I'll talk about a few of those. And there's something from way back that Einstein actually put into his equations called the Cosmological Constant. Okay, and for those of you familiar with calculus, it's really just a constant of integration in his equations, and he sort of omitted the cosmological constant. The idea of the constant is that as space expands, just the fact that you have more space means you have more energy, right? Because space isn't empty. Well, and we'll talk a little bit about how that could be as well. So this cosmological constant was in the Einstein field equations. But he omitted them. And in the end, when we found out that the universe was actually expanding, this cosmological constant would have actually predicted that the universe was expanding. And he actually called this to a friend of his, Gamow. He said that this was his biggest blunder, which is really too bad, because had he predicted the expansion of the universe, Einstein might have been famous, but he forgot to, he just decided not to put this constant in. Okay, so this is just a mathematical remnant, right? So we don't know really, this doesn't explain what it is. There's this idea, right, that, remember how we've talked about the fact that empty space is not, that space is not empty, right? We always have things, we can have things popping in and out of existence, right? So I can have my electron and my positron, and then they annihilate each other really shortly, and this is all has to do with the Heisenberg uncertainty principle. Okay, and as long as I have the energy for a short amount of time, I can have as much of it as I want to, but this is happening everywhere in space, so this could explain where this energy is coming from. This is called the vacuum energy, okay, and this is predicted by quantum mechanics. But if I look at what the vacuum, if I look at how much vacuum energy there is, if I do a calculation of how much there is per unit space, it turns out that there's 10 to the 120 times the amount needed to explain dark energy. So remember, dark energy is a lot of stuff. It's 75% of the universe is missing. If I try to use the vacuum energy to say, oh, let's say all the vacuum energy is the dark energy, it turns out that the number is huge. That's 10 with 120 zeros behind it. Okay, 120 zeros behind it. That's how much bigger the amount of energy is from the vacuum energy than than we need to even have dark energy. So it probably isn't this. And so this is sort of called the fine-tuning problem, right? So there's this idea of why is it exactly the amount of dark energy needed to make the universe sort of look flat and just be accelerating a little bit. Okay, and then the other part of the fine-tuning problem is, why is it happening now? Why are we right at the turnover? Why does it happen to be that as humans are trying to look to see when this is, it almost exactly is right now when we're looking for it? There's other ideas of what this can be. There's something called quintessence. Okay, and quintessence, in a simple way, is sort of a tunable vacuum energy. Okay, quintessence is from ancient use. It was the quintessence was the fifth element. So air and air, fire, water, earth, and quintessence. Okay, and which was actually in popularity in the late 1800s, and sort of physicists have introduced it again to try and be a type of vacuum energy that we can tune and have the right amount of it. Okay, and the truth is that we're really not sure what dark energy is. We have a lot less of an idea than dark matter. Dark matter could just be a particle, right? We have been finding particles for years. The last 30 years, we found more and more new particles. But this dark energy is such a weird thing, and there has to be so much of it, and we're just not really sure what to think of it. So there's lots of searches for the dark energy and how much there is. There's lots of searches for how much the universe is expanding and how much we really need. But the dark energy helps explain all the expansion and how the universe has evolved. And there's a couple of things here that to try and get around, a couple of ideas that people have used to sort of get around the fine-tuning problem. Okay. And one is this idea of the multiverse. So universe implies there's only one, multiverse implies that there's many, and that we just happen to be, right? There's all these bubbles expanding in different parts of whatever, and that there's many universes, okay? We just happen to be in the one that is good for life. It's good for life and has all of the physics that's the right way for all of this stuff to happen. So this is the idea of chance, right? That there's however many bajillion universes out there, and we're just in this one because this is the one that worked out for us. Okay, then there's another very similar idea called the Anthropic Principle. And this basically says that humans are here because we're here. You can see that's sort of a circular argument. The idea is that this universe worked out for life, okay, and the only reason that we're here to study it is because it worked out for life. If it hadn't worked out for life, then we wouldn't be here, and there would be nobody here to study it, okay? And these two ideas are not exclusive. It's not like there's one or the other. They sort of overlap with each other, okay? And I think they're very interesting ideas, and I'd love to actually have some discussions about this, but this is a great topic to sort of talk about. And this is really on the edge of where philosophy and religion meet physics. These are ideas that sort of physicists think of as cop-outs in the sense of, like, we can't test them. I can't test the multiverse idea. I can't test the Anthropic Principle idea, so I leave the realm of science. Okay, but these are the things that I want to tell you about that are sort of out there. They're also talked about in your book. Okay, and I want to sort of end with a little bit about where this evolution of the universe is going. Okay, so we have something now that's called the Lambda CDM model of the universe. Okay, and lambda is dark energy, because the lambda is the symbol that Einstein used for the cosmological constant, and then this is cold dark matter. Okay, and the thing is, right, is that right now the universe expansion is accelerating, but we don't know what will happen in the future. Happen to right in the future. And I sort of want to talk about the different ways that the different ways that the universe could evolve, right? The expansion could decelerate, okay? So I could have a deceleration of the expansion. Everything starts coming back to each other. There's enough mass somehow to pull it all back together, and this leads to a big crunch, right? And everything gets crunched back into something the size of the Big Bang. That's sort of number one. I could have everything accelerate, and when that happens, right, this is called the Big Rip, and this is so powerful, so this would pull quarks apart in the end, and maybe space-time. Okay, and so this is really, and this is what's already happening, right? This is what's happening. We know that the universe is accelerating. If I do the calculation, then I can get a number like 22 billion years when the acceleration will be so big that it would pull nuclei apart, right? That's when it will do this, pull the quarks apart, or at least pull the nucleons apart. That's a calculation by some folks at Caltech. That's the details of that, or a little more details are in your book if you want to look at that. Okay, so that's just like calculating what we already know is happening. Okay, but we don't know what's going to happen in the future because we don't understand a good chunk of the stuff that's out there, right? I think that's a really important thing to remember. And then 3, even if we sort of go on a steady state, just expanding sort of moderately, right? What will happen is eventually the hydrogen fuel will burn up in stars, and they'll go out. Even the dim, slowly burning stars will go out, and there'll only be rogue supermassive black holes. Which will eventually radiate. Away. Okay. And so that's even if we just expand moderately. Now, these all sound like horrible doomsday ends. Of course, they're so far away that none of us will see them. And there's all kinds of interesting ideas of what could happen. If we are in a multiverse, maybe we can get to another universe before something like this happens. We have a lot of billion years to keep evolving and figuring out technology and seeing what will happen. And this is, you can see why this is just really interesting and important for humans to try and figure out, right? We want to know what our fate will be, even if we won't be around to see it. Okay? And I don't mean this is not meant to be fatalistic. These are just the facts about what we know. These are the scenarios that we have. Now, of course, we don't understand everything, and there's a lot to understand. So maybe there's some other way of so there's something else that's going to happen in the future. So this is the current model of cosmology as we know it, and those are most of the details about what I want to tell you about the universe. In the next lecture, we'll talk a little bit about future research and reasons for doing it.